Given any line, like the one shown here in purple, it's often useful to be able to go through and find the equation for a line perpendicular to it. So for example, let's say we've got a line perpendicular to the purple one, like the one shown here in red. We'll notice that in most cases, one line will have a positive gradient and another line will have a negative gradient. The exception to this, of course, is with a horizontal line and a vertical line. Now there is a connection between the two gradients of the two lines, and the rule is that the gradient for one line is equal to the negative reciprocal of the gradient of the other line. And that's shown as m1 is equal to the negative of 1 over m2. Let's have a look at a proof of how we can actually show that. We'll keep our two lines and we'll form two right angled triangles. We've got an angle A in the left hand corner of the red right angled triangle. Because there's 180 degrees in the triangle, we can subtract A and 90 degrees, which is a right angle, from 180, and that gives us a result for B, which is 90 minus A. If we look at where the 90 degrees is, there's a straight angle formed from the connection of the purple and red horizontal lines. That means that the angle in the bottom right hand corner of the purple triangle must be B, because B is equal to 90 minus A, and the angle in the top left hand corner of the purple triangle is therefore A, by the similar properties of what's occurred in the red triangle. Now we're going to label the different sides of these right angled triangles M, N, P and Q. For no particular reason, they just represent the lengths of the sides of those triangles. Now in the red triangle, the tangent of angle A is equal to M over N, in other words opposite over adjacent. Now that also matches the gradient formula, because M and N match the rise over run for that section of the line. So that's also the gradient for line 1. Let's have a look at line 2 and also look at the tangent of angle A. In this case, opposite over adjacent gives us Q over P. Now it's the same angle, angle A, but in this case Q is the run of that triangle and P is the rise of that triangle. So we can make a connection between these two tangent formulae. We can look at tangent A for line 2 and compare it to tangent A for line 1. We can see that in line 1 tangent A is equal to, for line 1, rise over run. But in line 2 the reciprocals occurred, and reciprocal means the fraction has been flipped over. So the gradient of line 1 matches the reciprocal of the gradient of line 2. And as we said at the start of this piece, the gradients have opposite directions. So one is negative and the other is positive, or vice versa. So the final formula is the gradient for any line is equal to the negative reciprocal of the gradient for its perpendicular line. And the way we summarize that in a formula is to put m1, the gradient for a line, is equal to negative 1 over m2, where m2 is the gradient of the other line. We use this property to help us find the equation of lines perpendicular to other lines which are already known.